Okay, hello. This is the last of the videos for this week. So it's the video 4, and we're looking at activity 10-3. And there are a couple of things we're going to discuss in this video: post-hoc comparisons, SPSS output, and reported results in APA style. And this is the first part of the activity worksheet. It's actually a separate problem, just kind of a practice how you can just to kind of complete some of the calculations that you might expect to see. I expect you be able to do, and there might be maybe some similar problems on the exam and etc. So it's just basically a good practice. Problem number 1. Cognitive psychologist is interested in studying the influence of stress on reaction time. A sample of n equals 30, so total 30 participants. Randomly assign them to one of the 3 groups. And calm, stressed, highly stressed. Depending on the conditions, the participants are asked to watch a short film that is neutral, induce some stress, induce a lot of stress. Their reaction time was then tested, so the dependent variable was reaction time. Below are the summary statistics. SS total equals 18542. So this is SST. SST equals 18542. Now, sum of squares within the group of calm equals 5478. And for the stress group, 5347. For the highly stressed group, 5317. Okay, so this is the ANOVA summary table, and we need to fill out sum of squares, degree of freedom, mean squares, F, and find the p-value. Okay, so we already have the SS total. Now, if we add these 3 numbers together, that would give us SS within, right? So the sum of these 3 equals SS within. So if you add 5478, 5347, and 5317, SS within should equal, according to my calculation, should double check, equals 16142. Okay, 16142. Now, how do we calculate SS between? So it looks like we don't really have anything for SS between, but we do know that SST equals SSB plus SSW. So we can take advantage of this fact. We already know SST. We already know what SSW is. So SSB equals SST subtract SSW. So you should get 2400. That's SS, sum of squares between groups. Okay, so now we have SSB, SSW. What about degree of freedom? So degree of freedom between groups, that's the number of conditions, 3 minus 1, so 2. What is the total degree of freedom? That's n minus 1. 30 minus 1, 29. And how many degree freedom do we have for within groups? Well, that's easy. It's n 30 minus k 3, 27. Right? So you can double check 27 plus 2 equals 29. So now once we have the sum of squares, degree of freedom, then next step is just mean squares, right? You need to calculate mean squared between groups, mean squares within groups. No need to calculate that. And once you have the mean squares, you can calculate the F statistic. Once you have the F statistic, go to this website. And degree of freedom is 227, and you can find the corresponding p-value for the F statistic that you calculated. Okay, so I'll leave this to you to figure out what the answer is, and I'm pretty sure at this point, you will be able to finish the remaining of this summary table. Okay, so that's a practice of the omnibus F-test. Now, next, let's talk about post hoc comparisons. So remember that when we conduct the omnibus F-test, the null hypothesis simply says mu1 equals mu2 equals mu3. And of course, if you have other conditions, more than 3, then it equals everything equals mu of k. And the alternative hypothesis, you can say not all mu's are equal, or you can say mu of I does not equals mu k for at least some ik, which is just a more fancy way of saying somewhere there may be some difference. Okay, so it's the opposite of the null hypothesis. The null hypothesis says there's no difference whatsoever. Alternative hypothesis, so if we reject the null hypothesis, our conclusion is overall there is some difference. But that the overall test, the omnibus F-test, does not tell us where exactly that difference is. And that can be an interesting question. So if you think about the example, no phone, handheld, hands-free, right? So overall, we know there's a difference. However, we also want to know, does it make difference to use handheld and hands-free set? Right? So we want to know those more detailed information. And for that, we need to resort to something we call post hoc multiple comparisons. Sometimes we call this post hoc pairwise. Okay, so post hoc pairwise comparisons. And the reason it's called a post hoc is because we conduct this kind of comparisons only if the omnibus F-test is statistically significant. If there's no overall difference, then we don't have a reason to conduct this kind of post hoc pairwise comparisons. Okay, so that's why it's called post hoc. So only if the F-test is significant. And it's a pairwise comparison. So if we have 3 conditions, we're actually going to compare condition 1 versus condition 2, condition 1 versus condition 3, and then condition 2 versus condition 3. So it's a pairwise comparisons. And how many comparisons we need to conduct depending on how many conditions that we have. So if there's only 2 conditions, no need for post hoc pairwise comparison. If I have 3, we need to do 3 tests. If we have 4 conditions, we have to conduct 6 pairwise comparisons. 1 versus 1, 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. 6 comparisons. So the number of comparisons actually can go up pretty quickly as the number of groups that start to increase. Now, the problem with this kind of multiple comparisons is that it's going to lead to increased, we call that family-wise, or sometimes we call it experiment-wise type 1 error. So in other words, it's defined as the probability to make at least one type 1 error out of all these comparisons. So that's the pairwise, and so that's the, we call it experiment-wise or family-wise type 1 error. And there's the equation to do the calculation. You don't have to, we're not going to require you to do this calculation, but basically what you have is 1 minus alpha level, 0.05, and take the square of C. C refers to the number of comparisons. So if you run 3 comparisons, it's cube. It's to the power of 3. And if you do 6, it's to a power of 6. So basically, the alpha levels, the overall alpha level probability to make at least one type of 1 error is going to increase as the number of comparisons increase. Okay, so here's the thing. We don't like type 1 errors, right? We don't like type 1 errors. So we don't want to make, for example, 30% type 1 error. That's not good. So we want to control experiment-wise type 1 error. We want to avoid type 1 error. So the easiest way to control type 1 error is to conduct the test, the alpha, use alpha instead of alpha equals 0.05. We can conduct the test at alpha equals, for example, 0.01 or even 0.001. So if we conduct each comparison at alpha equals 0.01, for example, then if we only conduct 3 tests, then the overall type 1 error is not going to exceed 0.03, which is totally acceptable, right? And so we can control type 1 error by conducting essentially more conservative tests. However, the side effect is the problem with that approach. Remember our previous discussion, the discussion that we had prior to the first midterm exam, which is, what is the relationship between type 1 error and type 2 error? So if you try to control type 1 error by reducing the alpha level, it increases the probability of type 2 error. In other words, you lower the power of your test. And that's not good either. So we have these competing goals. One is to control type 1 error, and the second is to maintain adequate power. Okay, so we don't want to make too many type 2 errors as well. So what do we do? Well, statisticians have researched that question, this problem extensively, and as a result, they made a whole bunch of different recommendations, different methods of post-hoc comparisons. And so we are not going to discuss the technical details, but we just say, well, what are the choices? And the choices are, if you want to have more power, then we are going to make type 1 error. On the other hand, if you're going to have a better control of type 1 error, the power is going to suffer. So we want to find a compromise. Okay, so there are some methods that are designed to maximize power, but unfortunately, they also maximize type 1 error. And there are also tests like Bonferroni, which provides the best control of family-wise type 1 error. But on the other hand, this test has the least amount of power. So in between, we have a method called the Tukey's HSD. HSD, believe it or not, actually stands for honestly significant difference. So Tukey's HSD seems to strike a nice balance between maintain the power and also avoid try not to make too much type 1 errors. So if you use SPSS to conduct a F-test, analysis of variance, you can ask for post-hoc comparisons, and then you can specify Tukey's HSD as a method for post-hoc comparisons. Okay, and there's another method that also used, kind of also slightly more conservative than Tukey's HSD, is Chaffee's. Sometimes people use Chaffee instead of Tukey's SHD. Okay, so next, let's take a look at the SPSS output for one-way between subjects analysis variance. And this is the same data set, so you're going to see some numbers that you look very, very familiar. Okay, so this is what the SPSS output looks like. So first, you have descriptive statistics. Okay, so this is where you find the descriptive statistics. And you have the mean. Equals 4.00, 1.00, 1.00, and your grand mean, that's a total, equals 2.00. Number of participants, 555, total 15. And standard deviation, 1.22, 1.22, 1.00. And if you combine all 15, the overall standard deviation is 1.81. Okay, so When you report the results, remember, you need to report the mean and the standard deviations. If you are going to use a bar graph and you want to add, if you want to add the error bars, then use standard errors. Okay, but if you report descriptive statistics, it's mean and standard deviation. We don't really need to pay attention to confidence intervals or minimum, maximum, so just ignore those. Now, ANOVA. So this is actually pretty nice. This ANOVA table is in the exact format that we use for what we call ANOVA summary table, right? So we have a source, between groups, within groups, total, sum of squares, degree of freedom, mean square, F, and the level of significance, which is the p-value. Okay, so 11.25, p equals 0.002, kind of verify our calculation. Effect size. So we want eta squared. And we're just going to use the point estimate. So eta squared equals 0.65. So ignore this part. We don't need this part. We don't really need to pay attention to this part either. So just we can cross it out. Okay, so eta squared equals 0.65. 65% of the sum of squares of variation in the data is caused by between group variation. So it's a very large effect size. And we would report the F, parentheses, 2 degrees of freedoms, comma, space, 12. Equals 11.25. And p equals 0.002. Okay, so that's the omnibus F test. Now, pairwise comparison. So post hoc tests, dependent variable is the driving score, and the method that we used is Tukey's HSD. It's called a multiple comparison. You can call this pairwise comparison. The way to read this is this. So this is no phone condition and condition 1 compared to condition 2, right? So this is the first comparison. And you actually don't need to pay attention to anything else. The only information you need is in this row, in this column, sig, level of significance. In other words, the p-value. So anything with p-value less than 0.05 is statistically significant. Okay, so difference between no phone condition and handheld condition, condition 1 versus condition 2. Significant, right? P equals 0.004. Next, condition 1 with condition 3. So no phone versus hands-free. So condition 1 versus condition 3. P equals 0.004. Again, significant. Now, next we have handheld. So this is 2. 2 versus 1. It's redundant, right? We don't need this part because 2 versus 1 is the same as 1 versus 2. So, and what about this one? This is condition 2. This is condition 3. Okay, so that's new. We needed a comparison between condition 2 and condition 3. And this time, P equals 1.000. So P actually cannot equal 1.00, but it's very, very close to 1.000. Okay, so in other words, there was no significant difference between condition 2 and condition 3. Now, what about this last one? That's condition 3 versus condition 1. Redundant. condition 3 versus condition 2, redundant. So now we have everything that we need, right? So post hoc comparison, pairwise comparison tells us that the no phone condition was significantly different from the handheld condition p equals 0.004. It was also significantly different from the hands-free condition p also equals 0.004. However, there was no difference between handheld and hands-free condition. So that is the result of the post hoc pairwise comparisons. And by the way, for the post hoc pairwise comparisons, I do not require, there's no expectation that you do any kind of a hand calculation. The only thing I would expect you to be able to do is that if I give you a SPSS output, something like this, you should be able to interpret the finding, the result for post hoc pairwise comparisons. Okay, so for post hoc, it's more a matter of interpreting SPSS output rather than using the equation to do any kind of a hand calculation. So the last is report the results in in APA format. So you always describe the test. You report the statistics and you report the descriptives, the means and standard deviations. And if the effect was significant, effect size. And also these are the some guidelines about SPSS format, the APA format. Always double space, results as a level 1 heading, italic font type, if you have F, P, M, standard deviation, etc. And round the numbers to 2 decimal points, except when reporting the p-value. If you're reporting the p-value, you can report 3 decimal points. More than that is less than 0.001. And here's an example. So the first sentence gives you describes the test. Next, omnibus F test. So F p-value. Eta square equals 0.65. And we can just go with eta square instead of a partial eta square. We can do this after we come back from spring break. We can talk about the difference between eta squared and partial eta squared. For between subjects ANOVA, there's no difference. They're always the same. But for within subjects ANOVA, within groups ANOVA, eta squared and a partial eta squared is going to be different. And so here we can just stay with eta squared. So equals 0.65 effect size. And then you report the post hoc comparisons. So again, you describe analysis. Post hoc comparisons using Tukey's HSD can be specific about what methods you used. Indicated that driving performance was significantly higher in the no phone condition M, the mean, standard deviation, than in both the handheld condition, mean, standard deviation, and the hands-free condition, mean, and standard deviation. P equals 0.004. The reason is PS is plural because there were 2 p values, right? So the first p is italicized. Second S is not because S means plural. So that's not a statistics symbol. And then you say the difference between the handheld and the hands-free conditions was not significant. P equals 1.00. So that concludes the entire write-up for the for this ANOVA omnibus F test and the pairwise post hoc comparisons. Now, here we only presented 3 sets of mean and standard deviation, so it's still easy enough to report all of these in the text. But if you have more means and standard deviations, you should probably create a table. So in this case, I think you don't have to use a table. Now, there's nothing wrong if you want to use a table, but it's just not that necessary. Okay, so this is the end of activity number 3. and just follow the instructions. This part, you can feel free to use this as an example, use this as a template. You don't have to say things exactly the way I said it, but you need to include all these information. And also don't forget the level 1 heading, right? Results. And that's centered and in bold font. Okay, so that is the end of this entire set of this video. And so don't forget about the homework for this week, and they are all due on the 30th. All 3 activity worksheets are also due at the same time. Okay, so feel free to let me know if you have questions. I will still check my email, and my reaction time, my response time may be a little longer than usual, but I should be checking my email. Okay, so I wish everybody have a great spring break, and I'll see you back in classroom after the spring break. Okay, goodbye.